Imagine you're trying to teach a toddler calculus, right? And every time they make a single mistake, you just scream at them.
Yeah, that's a terrible strategy.
Right, they'd panic. The learning process would completely collapse and they'd probably just start crying. Well, that is exactly what standard on-policy distillation does to small language models.
Basically, yeah.
Welcome to AI Paper Slop. Today we are looking at a paper titled Trust Region Policy Distillation, or TOPD, by Zhengpeng Shi, Li, Lina Zhang, Zeke Shi, and Mao Yang.
It's a fantastic paper.
It really is.
Yeah.
So if you're doing post-training for large language models, you know that standard on-policy distillation, OPD, is notoriously unstable and just highly sample inefficient.
Completely.
This paper introduces TOPD to solve these exact issues with two main mechanisms. First, an external proximal teacher to mathematically bound gradient variance, and second, internal trust region iterations for safe, off-policy data reuse.
Which is huge.
Exactly. The bottom line for your training runs. You get guaranteed monotonic improvement, literally zero extra compute overhead, and a massive 25.8% absolute gain on the AIME24 benchmark over standard OPD.
Yeah. I mean, it is a phenomenal piece of engineering. Because, well, it directly tackles a structural bottleneck that's been driving practitioners crazy during alignment and post-training.
Right. The landscape right now is pretty brutal.
It really is. If you look at the current paradigms, you're essentially stuck between two flawed options. On one side, you have supervised fine-tuning, SFT.
Which is stable, but...
Exactly. It suffers heavily from catastrophic forgetting because you are just blindly forcing the model to mimic trajectories.
And on the other side,
you have reinforcement learning with verifiable rewards, like RLVR. Now, this avoids the forgetting issue, but it suffers from sparse sequence-level rewards.
Like a binary pass-fail at the end of a long test.
Right. It's incredibly difficult for a model to optimize its reasoning when it only gets a thumbs up or thumbs down at the very end of this massive chain of thought.
Yeah. Which is exactly why the industry started moving toward OPD. You want a signal at every single step of the generation.
Conceptually, OPD is the perfect bridge. It provides that dense supervision step by step without the rigid mimicking constraints of SFT.
But the math is broken, right?
Basically, yes. The core problem this paper exposes is that the underlying mathematics of standard OPD are fundamentally broken when deployed in practice.
Okay, wait, break that down for me. If standard OPD is supposed to give us these beautiful, dense token-level rewards, what is structurally breaking when you actually run the code?
It comes down to the optimization objective. Specifically, the reverse KL divergence. In standard OPD, your immediate token level reward is defined by a logarithmic probability ratio.
Between the teacher and the student.
Right. Mathematically, you are taking the log of the teacher's probability divided by the student's probability for any given generated token.
And this is where we hit what the authors call the capacity gap. Because, you usually have a massive teacher model, say 30 billion parameters, and a much smaller student model.
They have vastly different internal representations, yes. The teacher has a much richer vocabulary distribution, a deeper understanding of context.
So what happens when they disagree? Like, what if the student takes a reasoning path the teacher would just never take? Let me ask about the math there.
Go for it.
What happens mathematically when the student generates a token, but the target teacher assigns that token a probability of effectively 0?
Well, you run into the optimization equivalent of dividing by 0.
Oh, wow.
Yeah. If the teacher's probability for a specific token approaches 0, the entire ratio approaches 0. And the logarithm of a number approaching 0 diverges to negative infinity.
So your token level reward isn't just a gentle nudge saying, hey, bad token.
No, it becomes an infinitely large penalty, an unbounded penalty.
Which completely destroys the policy gradient.
Exactly. The immediate reward diverges to negative infinity, which causes the gradient variance to violently explode. The optimization process just becomes completely unmoored.
So the student model's weights essentially get shredded by these unbounded updates.
Shredded is a good word for it, yeah.
Now, if you're training these models, you've probably tried to patch this. Like, the standard industry fixes right now are things like reward clipping or top sampling to artificially restrict the vocabulary.
Teacher-student mix sampling is another one, yeah.
Right. Why aren't those enough? Why do we need a whole new framework?
Because, honestly, they are just empirical heuristics. They're Band-Aids on a broken bone.
Just taping it up?
Exactly. If you clip the reward, sure, you might stop the gradient from literally overflowing into nans and crashing the whole run, but you fundamentally distort the true distillation signal.
The math no longer represents the actual divergence.
Right. None of those workarounds offer any rigorous theoretical guarantees. You're basically just rolling the dice and hoping you tuned your clipping hyperparameters well enough to survive the epoch.
Okay, so since we can't just slap a Band-Aid on it, we have to fundamentally change the target. How does TOPD construct a target the student can actually hit?
This brings us to their first core contribution, the external proximal teacher.
So instead of a rigid target, they use a surrogate.
Exactly. A target that's closer to what the student can realistically achieve. TOPD constructs this proximal teacher by interpolating between the probability distribution of the true teacher and the probability distribution of the current student policy.
So you're dynamically meeting the student halfway. It's alpha times the teacher's probability plus 1 minus alpha times the student's probability.
That's the exact formulation.
Yeah.
And the mathematical elegance of substituting this back into the reward function is really striking.
I have a question about that, actually. When you look at standard distillation code, it almost always operates in log probability space.
Yes, it does.
If I were trying to implement an interpolated target, my first instinct would be to just interpolate those log probabilities. Does doing it in linear probability space change things?
It changes absolutely everything. You've identified the exact mechanism that makes TOPD work.
Oh, really?
Yeah. If you were to interpolate in log probability space, which, is a super common intuitive mistake, the resulting reward would just be alpha times the original standard OPD reward.
Which is just a naive scaling. Alpha times negative infinity is still negative infinity.
The variance would still explode, it would just happen slightly slower. The bounds would still be broken.
But by doing it in linear space...
Exactly. By doing it in linear probability space, before taking the logarithm, you introduce an additive constant inside the log. The new token level reward becomes the log of alpha times the original probability ratio plus 1 minus alpha.
Oh, okay. That plus 1 minus alpha term is the magic key.
It is the entire foundation of the first pillar.
Because even if the teacher's probability is a hard 0, the term inside the logarithm is bounded by 1 minus alpha.
Exactly. It caps the penalty. It creates a strict lower bound, meaning the reward can never go to negative infinity. The maximum penalty is just a log of 1 minus alpha.
That's so clean. And it's not just a guess, right?
No, not at all. They rigorously prove this in Theorem 4.2. They demonstrate analytically that the variance of the gradient estimator is strictly bounded by an absolute mathematical limit across the entire space.
So the variance explosion is theoretically prevented from ever occurring. That makes the alpha parameter incredibly important then.
It gives you explicit mathematical control over the trust region of the gradient.
So if you set alpha to 1.
Well, the 1 minus alpha term disappears.
Yeah.
The proximal teacher just becomes the original rigid teacher, and you recover the explosive variance of standard OPD.
And if you swing it the other way, like alpha approaches 0.
Then the proximal teacher becomes the student itself. The gradient variance vanishes entirely, but your model wouldn't learn anything because it's just imitating itself.
Right, right. So where's the sweet spot?
In practice, the authors found that setting alpha to 0.1 or 0.2 provides the optimal balance. You get strict variance control while maintaining a very strong learning signal.
Okay, so Pillar 1 solves the optimization fragility. But stopping the gradients from exploding is really only half the battle here.
Right, because of the sample inefficiency.
Exactly. Standard OPD is strictly on policy. Generating rollouts from a massive LLM is super expensive, and standard OPD just throws that data in the trash after one update.
It's remarkably wasteful. You're constantly bottlenecked by data generation. This is, the exact same problem standard policy gradient methods faced years ago, which led to PPO or TRPO.
Let's use a gym analogy. Standard OPD feels like loading up a heavy barbell, doing exactly 1 rep, taking all the plates off, and completely re-racking the weight.
That is a perfect analogy, yeah.
You're doing way more work setting up the data than actually training.
No.
So TOPD says, hey, while the weight is on the bar, why don't we do a full set? How do they achieve this data reuse?
They introduced their second pillar, which is internal trust region iterations. Inspired by PPO, TOPD decouples the behavior policy, the model state that generated the data from the target policy, which is actively being updated.
Okay, so during the rollout phase, they don't just generate one response.
No, they generate a group of multiple responses per prompt. In their main experiments, they use a group size of 8.
So we keep those 8 responses and perform multiple internal epochs on them. But wait, if we blindly iterate on reused data, don't we risk over-optimizing to that batch?
You do.
To extend that gym analogy, if we do a full set with heavyweight, we need a spotter, right? So we don't diverge from the policy entirely.
The spotter here is the trust region itself. When you reuse off-policy data, you have to use important sampling to correct for the fact that the policy is changing.
But important sampling can also suffer from variance explosion.
Exactly, if the new policy drifts too far. So TOPD employs a clipped surrogate objective during these iterations, very similar to PPO. It mathematically prevents the student policy from updating too far away from the data gathering policy in any single epoch.
That makes sense. I noticed a really subtle detail, though, about how they handle advantages during these iterations.
Oh, the token level normalization.
Yeah. In standard RLVR, you typically normalize the advantage at the sequence level, looking at the whole response. Why token level specifically here?
Well, a sequence level advantage is great for sparse rewards, but it suffers from a massive credit assignment problem.
Like, if a model writes a brilliant paragraph but makes a fatal math error on the last token.
Precisely. A sequence level reward struggles to isolate which specific token caused the failure. Because TOPD is built on dense token level rewards, it needs token level normalization to fully exploit that signal.
It evaluates the relative quality of specific tokens compared to alternative paths at that exact step.
Right, which prevents the model from developing weird gaming behaviors.
Like generating overly short responses just to dodge potential penalties later.
Yes, or generating excessively long, rambling responses to farm small, incremental positive rewards.
Got it. Okay, so this brings us to the theoretical closed loop connecting these two pillars, which is theorems 4.4 and 4.9.
This is arguably the most beautiful part of the paper's math.
Let me make sure I have this right. The paper states the proximal teacher creates a bound on the convergence gap. But how do the internal iterations actually close that gap mechanically?
So theorem 4.4 abstracts the proximal teacher into an iterative operator. It proves that the asymptotic convergence gap, the theoretical distance between your fully trained student and the optimal teacher, is strictly bounded by epsilon infinity divided by alpha.
And epsilon infinity is the single-step optimization error, right? Like the local error from optimization noise.
Correct. So look at that fraction. Epsilon infinity over alpha. If you want your student to perfectly match the teacher, you need that gap to be as close to 0 as possible.
But you can't raise the denominator alpha towards 1.
Exactly. If you increase alpha, you ruin the stability we just fought for in Pillar 1.
You'd be right back to the exploding variance of standard OPD.
So since you cannot raise alpha, the only mathematically viable path to closing that convergence gap is to brutally minimize the numerator.
The single-step optimization error, epsilon infinity. And that's what the trust region iterations do.
Yes, theorem 4.9 establishes that. By performing multiple internal optimization epochs on the decoupled data, by squeezing every drop of gradient signal out of that trust region with your spotter, you guarantee monotonic policy improvement.
It's a perfectly closed theoretical loop. Pillar 1 stops the explosion. Pillar 2 drives convergence.
It is incredibly elegant.
It is. But, I mean, if you're an ML engineer listening to this, you want to know if it actually trains better models and if it's going to cost a fortune in compute.
Well, the compute overhead is literally 0.
Literally 0. Wait, how is that mechanically possible when you're introducing a dynamic target?
Because the proximal teacher isn't an actual separate neural network doing forward passes in the training loop.
Oh, I see.
It is literally just a simple algebraic transformation applied to the existing token level reward equation.
So you're just running a few extra lines of math on the logits that are already sitting in VRAM.
Exactly. It's completely plug and play. If you have an existing pipeline built on Megatron LM or VLLM, you can drop TOPD in without requisitioning a single extra GPU.
Wow, that is massive for real-world adoption. Okay, let's look at the actual performance numbers then. They tested this heavily on math reasoning, right?
Yes, the DPO Math 17K dataset. Math reasoning requires long chains of thought, so dense rewards are crucial.
Walk us through the flagship result. What was the setup?
They used a Qwen 3 8B base model as a student, and they distilled knowledge from the Qwen 330B A3B instruct teacher.
And they tested on AIME 24.
Yes, a gold standard for complex math. Under standard OPD, the student model achieved an average pass at 32 accuracy of 24.58%.
And under TOPD.
Using the exact same dataset and teacher, TOPD hit 50.42%.
Wait, really? That's a 25.84% absolute improvement, not relative absolute.
It's a staggering leap. You literally double the reasoning performance just by changing the reward math to bounded linear interpolation and doing off-policy iterations.
It definitely proves standard OPD was leaving immense amounts of reasoning potential on the table. The gradients were just too noisy.
Absolutely. And they didn't just test against standard OPD. TOPD utterly dominated the heavyweights in the RLVR space too, specifically GRPO and DAPO.
Unpack those baselines for us real quick. Why did TOPD beat them so handily?
Well, GRPO and DAPO are state-of-the-art RL methods that rely on verifiable rewards, like checking if the final math answer is correct.
But they rely on sparse sequence-level signals.
Right, so they struggle with credit assignment during long reasoning chains. TOPD beat DAPO by over 17 absolute percentage points on AIME 24. By safely exploiting dense token-level rewards, it guides the model step by step.
Okay, so what happens when we push this to the absolute limit? We talked earlier about extreme capacity gaps. What if we scale the student down to the tiny Quen 3 1.7b base model?
This is where standard OPD completely disintegrates. The architectural difference between a 30B teacher and a 1.7B student is so severe that vocabulary mismatches are constant.
The unbounded penalties just shred the process.
In this regime, standard OPD actually performs worse than the RLVR baselines. It degrades to about 8.9% accuracy.
So the math literally breaks the model. How does TOPD handle that extreme stress test?
It holds the line beautifully. Because the gradient variance is strictly bounded by alpha, TOPD pushes that tiny 1.7b model past the 20% accuracy mark on AIME 24.
An 11.35% jump over standard OPD in a regime where standard OPD basically ceases to function.
Exactly.
Whenever I read these papers, I always jump straight to the ablation studies. You want to see what happens when you start turning off the specific mechanisms.
Oh, the ablations are very revealing here.
Like if you turn off the proximal teacher, say by setting alpha to 1.0, what happens mechanically?
The training curves show immediate violent instability. The loss spikes erratically, gradients explode, and final benchmark performance degrades severely.
So mathematical bounding mechanism is absolutely critical.
You cannot survive the dense reward signals without it.
And what if you keep the proximal teacher, but you disable the internal off-policy iterations? You just go back to throwing data away after one step.
The sample efficiency falls off a cliff. The model requires vastly more training steps and significantly more generated data just to slowly climb the performance curve.
Which proves the internal trust region is essential for driving down that single-step error. You mentioned earlier that alpha is typically set between 0.1 and 0.2. Is this one of those notoriously brittle algorithms where a slight tweak ruins the whole run?
Not at all. The framework is highly robust. They found virtually no difference in stability or performance when varying alpha anywhere between 0.1 and 0.3.
That's great. You don't need to waste resources on massive hyperparameter sweeps.
You said it, and the math does the heavy lifting.
So, to summarize the synergy for you, TOPD solves the two biggest headaches in policy distillation. It uses an external proximal teacher to strictly bound gradient variance in linear probability space.
Ensuring your training doesn't explode when the models disagree.
Right. And it uses internal trust region iterations to safely reuse off-policy data, guaranteeing monotonic improvement while boosting sample efficiency. Double the gains for zero extra compute.
It's a rare masterclass in fixing a fundamental mathematical flaw with rigorous theory that directly translates to empirical dominance.
It really is. It leaves me with a final provocative thought to ponder, actually. If TOPD can handle massive capacity gaps this cleanly, like bridging 30B directly to 1.7B, what are the actual limits?
That's the million-dollar question.
Right. Could this algorithm enable a near future where we distill 400 billion parameter foundation models directly into tiny edge device models in a single leap?
Skipping the intermediate stepping stones entirely.
Exactly. What is the absolute theoretical limit of the capacity gap before even bounded variance isn't enough to transfer the knowledge?
Given how clean these optimization bounds are, finding the failure point of that capacity gap is exactly what the open source community is going to be testing next.
Absolutely. Well, thank you for joining us for this deep dive into the source material on AI paper slop. As always, we highly encourage you to go read the full paper to explore the mathematical proofs of the theorems we unpacked today. See you next time.